In today's lecture, we are going to start higher order differential equations. Higher order ODEs. In fact, higher order linear ODEs. Previously, we defined an nth order ODE in this way, and nth order ODE is in fact defined as a n of x dn y by dxn plus a n minus 1 of x dn minus 1 y by dx n minus 1 plus so on plus a2 of x and d square y by dx square plus a1 of x dy by dx plus a naught of x. There is no d here. It's only y, or you can say d0 of y by dx0, or simply y of x, in fact. And right hand side is some function of x, f of x. So this is, we call it equation 1. This is linear nth order non-homogeneous ODE. I hope you know what is non-homogeneous. If the right hand side function is 0, then it is called non-homogeneous. If the right hand side function f of x is 0, then this equation 1 is called homogeneous. I told you earlier. Homogeneous nth order linear ODE. This is simply equations. If we define initial conditions along with this differential equation, it becomes an initial value problem. So what were the initial values or initial conditions? If we define initial conditions along with this ODE, how many initial conditions do we need here? Because the equation is of n order, then we need n initial conditions along with this differential equation in order to make it an initial value problem. What could be the initial values here? Y is a function of x. Y is a function of x. And let us assume that the domain of x is between a to b, okay, which is an interval is a subset of R. Okay. Now, initial value of the independent variable is A. So all the initial conditions should be at the initial value. So the first initial value could be y of A is equal to some alpha 1, or you can say if there is no derivative here, so we put here a 0 maybe, or you can start with the 1 maybe, whatever you like. Let's start with it 0 so that the notations remain compatible. The second condition should be on the derivative at the initial value. It could be alpha 1 and so on. How many conditions do we need until n minus 1th derivative at A, and it should be alpha n minus 1, where alphas, alpha 1, alpha 2, so on, alpha n minus 1, they are arbitrary constants. They could be alpha 0, alpha 1, alpha 2, so on, alpha n minus 1. They all are arbitrary constants.
Excuse me, sir.
And G beta.
So could you please repeat this point? I don't understand how we've gotten the initial conditions.
For any differential equation, in order to obtain the initial value problem, we define initial conditions along with the differential equation. And how many initial conditions do we define? We need n initial conditions here because the order of the differential equation is n. initial conditions should be equal to the order of the given differential equation. So here, order of the differential equation is n, so we need n initial conditions. Why is it so? Because you might have seen that while solving first order ODEs, we need to define only one initial condition. Why? Because after, in fact, what is our purpose while solving differential equations? We find the original function y. Okay. In order to get y, if we have first order differential equation, we have to eliminate the derivative. We have to integrate that equation in order to get y and in order to eliminate the derivative. So we get one integration constant. In order to find the value of that integration constant, we use one initial condition. So if we have second order initial value problem, we need two initial conditions because second order derivative should be integrated 2 times in order to get y. Okay, the reverse of that second derivative, we have to take 2 times integrations. So the solution of that differential equation should involve 2 integration constants or 2 arbitrary constants. So in order to find the values of those 2 arbitrary constants, we need 2 initial conditions. So that is the same applies here. If we have n derivatives, then in order to get y, the original function from this equation, we have to integrate this equation n times, which involves n parameters or n integration constants. And in order to find those constants, we need n initial conditions. When will the quiz start? 8:45.
Thank you so much, sir. It's clear now.
Okay, I hope you get it. So that's why we need n initial conditions in order to get n parameters, which are involved in the solution of this differential equation. Now, this differential equation, when do this differential equation have unique solution? When we would be sure that this differential equation must have solution. There are certain conditions on the first order initial value problem, as well as second order and so on, nth order initial value problem. When we are sure that this differential equation along with these initial conditions, this in fact the whole problem, when do this have or you can say when this problem must have unique solution. There are certain conditions on the coefficient functions. Here the coefficient functions are an of x, n minus n of x, a2 of x, and so on, a naught of x, and the right hand side function f of x. There are certain conditions on these functions. What are those conditions? It's been already proved that if the coefficients, if you can write here existence of unique solutions of one along with initial conditions, along with ICs. This means that we need to be sure before solving any order differential equation, we need to be sure that this problem must have a unique solution. Okay, because if the problem doesn't have a unique solution, then there must be some problem with the model. We have to go back and adjust or rectify the model, and then we try to solve it. Okay. If an of x, an minus 1 of x, so on, a naught of x, and the right hand side function f of x, they are continuous Continuous, I hope you know what is continuous function. You must have studied in calculus. Are continuous on the domain. What is the domain? On A, B. Yes, which is the domain of facts. If all these functions are continuous, the first condition, and an of x is not equal to 0 for all x belongs to AB, then equation 1 and 2, I can say it 2, along with 2, in 2 we have initial conditions. Then equation 1 along with 2 must have unique solution. So this is the criteria for a given initial value problem to must have a unique solution. Okay, for any particular problem on which you are working on a physical problem, what do you expect? You need to have a unique solution. Okay, if you have infinite many solutions, then you would be confused which solution is for our situation. Okay, so you must have only one solution which fits to your problem, to your physical phenomena, or to your application. So there is this is very important to know before solving a differential equation that whether this given problem has unique solution or not. Okay, so that's why we need to check whether these conditions are satisfied for the given problem. Then we are safe, we are comfortable that what we are going to do, we are going to solve this differential equation, it will have a unique solution. Otherwise, you would remain confused whether we are doing correct, whether we are solving this differential equation, whether it would have a unique solution or not. Okay, so we need to be sure before solving it that it has solution, it has unique solution. I hope you get it. If you have any question, you can ask me. One more thing which is obvious in this setting, which is not mentioned here, that is obvious. Okay, you have to do it. First of all, there must be some function which we are going to verify that whether this is a solution or not. Okay, and then we'll try to find whether this solution is unique or not. In some cases, in exercises, maybe they'll ask you whether this given function is a unique solution of the given differential equation or not. Okay, then what we need to check, for example, we say that, let me do this with the help of example. Just one, maybe. Variable x minus y is equal to 0 is the differential equation subject to IC's, sorry, CI is not, subject to IC's initial conditions. What are the initial conditions? Y of 0 is equal to 0 and y dash at 0 is 1. Now, prove that y of x is equal to 1 by 2 e raised power x minus e raised power minus x is the unique solution of maybe 1 is this, and this is 2. Unique solution of the problem, initial value problem, maybe initial value problem 1, 2. Now, in order to verify that this problem 1 and 2 has unique solution or not, we don't need this function. Okay. In order to prove whether this differential equation has unique solution or not, we don't need any function. Okay. How can we do it? We'll check the coefficients of here we have coefficient 1 minus here we have coefficient 0 of y dash minus or plus minus 1 of y equal to 0. This is your general nth order or second order differential equation along with these initial conditions. We need to check whether this differential equation along with these initial conditions, this problem must have unique solution or not. What we need to check, we need to check those above two properties which I told you earlier. What? A2 of x, here it is what? 1. A1 of x, it is 0. And A0 of x is -1. Okay. And A2 of x is not equal to 0 for all x belongs to R. Whatever the interval is, because here the domain of this differential equation is not given. If the domain is not given, then obviously you must consider the domain to be a whole set of real numbers. Okay. So whether, and the right hand side function is 0. Now, whether all these functions, these and this one, all they are continuous on R. Do they have any breaks or any discontinuities on R? No, they are continuous on R, all these functions. In addition, the coefficient of the highest order derivative in that equation is not 0 for any value of x. Both conditions have been met. Therefore, according to that setting or that theorem, that was a theorem which I told you. Therefore, equation 1 along with 2, therefore, IVP 1, 2 has a unique solution. Okay. Now we are sure whether this problem has a unique solution or not. It has unique solution. Now, what we are going to prove whether this function is a solution of this differential equation or not. If it is the solution, then this must be the unique solution. There must be no other solution of the given problem. Okay. How to check whether this function is a solution of this differential equation or not? We just insert this function into this differential equation. If this differential equation turns into an identity, then this function will be the solution of this differential equation, along with one more thing. This function should satisfy these initial conditions as well. Okay, so this function must satisfy equations as well as all the initial conditions defined in that problem. Now we are going to verify whether this function satisfies this differential equation first, and then we'll see whether this function satisfies these initial conditions as well. Okay, then we can say that this function is the unique solution of the given differential equation along with the initial conditions. Okay, I hope you get it. If you have any question, you can ask me. Now we are going to prove whether this function satisfies the differential equation. What is the function? The equation is nothing but y double dash minus y is equal to 0, and the function is y of x is equal to 1 by 2 exponential of x minus exponential of negative x. What do we need here in order to insert this function into this equation? We need second derivative of this function. So we need to take the derivative. First derivative is what? 1 by 2 e raised power x plus e raised power minus x. And the second derivative is 1 by 2 e raised power x negative e raised power minus x. So this is the second derivative. I hope you can take the derivatives. Now, second derivative, put it here, and y, put it here. So you can see that y double dash is exactly same as y. So they both cancel each other and we get 0. Okay. You can see that these two are exactly identical. We must have 1 by 2 e raised power x minus e raised power minus x minus 1 by 2 e raised power x minus e raised power minus x. So this can whole be cancelled with this one. And what do you get? Equal to 0, which is equal to 0. Okay. And the equation has become an identity. Therefore, this solution satisfies the given ODE. Therefore, y of x satisfies equation 1. Now, what is the next step? We need to satisfy, we need to check, we need to verify or check whether y of x, which is 1 by 2 e raised power x minus e raised power minus x, satisfies y of 0 is equal to 0, y of 0, the initial condition, satisfies the ICs of the given problem. How do we check it? We need to check y at 0. Y at 0 is what? What is your y of x? You put 0 here, e power 0 minus e power 0. 1 minus 1, which gives us 0. And we need to check y dash at 0. Now, what is y dash? Y dash is here, 1 by 2 e power 0 plus e to the power 0. It is 1, 1, 2, 2. Cancel out, we get 1. It means the given function, which we are going to prove whether this function is a unique solution, it satisfies all the properties of the theorem, as well as this function satisfies the differential equation and initial condition. Therefore, this function is a unique solution of this differential equation. Whatever the differential equation is, this is the procedure of verifying whether the differential equation, initial value problem has unique solution or not. And then for a given function, this is how we check whether that function is a unique solution or not. If at some point the coefficient function a2 of x at some value of x, if it becomes 0, then the order of differential equation has been reduced at some point. That's why we must have that the coefficient of the highest order derivative must not be 0 for any value of x. If it becomes 0 for any instant of x, then at that point, the order of differential equation will be reduced. That will no longer be an equation of the same order at that point within the domain. So the coefficient must not be, the coefficient of the highest order derivative should not be equal to 0 at any value of x. Okay, I hope you get it. If you have any question, you can ask me. There are several other examples given in my notes. You can try them. Um, Another special case of that theorem is that theorem is if f of x, capital F of x is 0, means the initial value problem is homogeneous differential equation. Then, or you can say for homogeneous ODE, y is equal to 0 is always the solution of homogeneous nth order linear differential equation. Is always the solution. Y is equal to 0. Y is equal to 0, which is called trivial solution. It is always the solution of the given homogeneous differential equation, but only for the equation, not for the initial value problem. For example, we have this differential equation, but you have to be very careful while checking whether y is equal to 0 is a solution of this differential equation or not, whether it is homogeneous or not. If we have only this differential equation, y is equal to 0 is solution. It satisfies the equation. Okay. Now, let's come to the initial conditions. If we put here, if these are the initial conditions, then y is equal to 0 still satisfy these initial conditions or not?
No.
No, because y is equal to 0. If you have y of x is equal to 0 always, for all values of x belongs to R, then y dash of x is always 0 as well. But this condition is satisfied, but this condition is not satisfied because the derivative at 0 is not equal to 1, according to our trivial solution. So this solution does not satisfy this initial condition. So a homogeneous, if we have a homogeneous differential equation, then y is equal to 0 is always the solution. If we have only the equation, if we have initial conditions along with this problem, then we have to be very careful in saying that y is equal to 0 is the solution of this an initial value problem, because the solution should satisfy the initial conditions also. If it doesn't satisfy, then we cannot say, or we should say that y is equal to 0 is not a solution of the given initial value problem. Okay, so satisfying initial conditions is equally important as the function should satisfy the ODE itself. We have to check all these things in an initial value problem, that the given solution must satisfy ODE as well as initial conditions. Okay, so for homogeneous ODE, nth order linear ODE, whatever the ODE is, y is equal to 0 is the trivial solution when the initial conditions, it satisfies also the initial conditions. Okay, if we take it here, while dash is equal to 0, then y is equal to 0 is the unique solution, of the given initial value problem. Then we cannot say that this will also be a solution, because we are saying that if the differential equation satisfies certain conditions, it must have a unique solution. If y is equal to 0 is a solution, then this can't be. So the initial value problem must have unique solution. Either it is trivial solution or it is some other solution. Okay, so remember these things while defining solutions for homogeneous as well as non-homogeneous initial value problems. I hope you get it. If you have any question, you can ask me. There are certain examples as well as exercises. I hope you can do it. Another example, maybe x minus 2, y double dash, plus 3y plus 3y is equal to x, along with the initial conditions y of 0, 0, y dash of 0 is 1, y of 0 is equal to 0, and y dash of 0 is equal to 1. Now, this differential equation, for what value of the x, or you can say for what interval this problem, initial value problem, has a unique solution. Again, we write the coefficient functions a2 of x, it is x minus 2. a1 of x is 0, and a0 of x is 3. And the right-hand side function f of x is x. And we take for all x belongs to R. Now, this is the problem. Can you check whether this problem has a unique solution or not? On R. If it doesn't have unique solution on R, then can we take any subinterval of R on which this problem has a unique solution? Sometimes a problem may not have a solution on R, but it may have a solution on a subset of R. Okay. Now, this equation, this a2 of x is 0 at x equal to 2. And the second condition we have written there in that theorem is that a2 of x should not be equal to 0 at any value of x. But this is a2 of x is 0 when x is 2. So this problem doesn't have any solution, unique solution on R, because it is 0 at some particular value of x, which is x equal to 2. It should not be 0 for any value of x. Now, I'm going to narrow down this interval. Now, I say that let's check on negative infinity to 2, this interval. Now, this function is not 0 for any value of x belonging to this interval. Okay. On this interval, a2 of x is not equal to 0 for all x belonging to negative infinity to 2. Now we can check whether the given differential equation, or sorry, given initial value problem has unique solution on this interval or not. Then there is a unique solution. We can prove all the two properties or both properties of the theorem that this differential equation will have a unique solution on this interval. Okay, because on this interval, all the coefficient functions are continuous. Right-hand side function is a continuous. Okay, on this interval, and the coefficient of highest order derivative is not 0 for any value of x in this interval. Therefore, the given problem has a unique solution on this interval. Okay, I hope you get it. There are some exercises. Try to do these exercises yourself. No, it's not a condition. Now, this is non-homogeneous initial value problem, linear second order differential equation. Okay? Linear second order initial value problem, and it is non-homogeneous. It may be homogeneous, it may not be homogeneous. But if it is homogeneous, for example, if it is 0, then homogeneous linear ODEs ODEs always have a trivial solution, but this is initial value problem. It doesn't have trivial solution as a solution, unique solution of this problem, initial value problem. Okay. Ji Abdul Mois Khan, raise the hand. जी.
इसमें मैंने पूछा था कि 2 से लेके इंफिनिटी वाले इंटरवल पे भी इसका एक यूनिक सॉल्यूशन एग्जिस्ट करेगा?
नहीं,
2 से लेके इंफिनिटी तक, नॉट इंक्लूसिव ऑफ 2?
नहीं करेगा. अच्छा, 2 से लेकर इंफिनिटी तक सॉल्यूशन एग्जिस्ट नहीं करेगा, क्यों? सॉरी,
कोएफिशिएंट तो लाइक कोएफिशिएंट तो जीरो नहीं होता ना, मतलब लाइक कंटीन्यूअस नहीं होता. x की वैल्यूज को भी हम 2 से ग्रेटर लें तो ये पॉजिटिव नहीं आएगा?
आएगा, सब कुछ ठीक है. एक मसला है सिर्फ, देयर इज ओनली वन प्रॉब्लम विद दिस इंटरवल. व्हाट इज दैट प्रॉब्लम? इस इंटरवल पे इस इनिशियल वैल्यू प्रॉब्लम का यूनिक सॉल्यूशन एग्जिस्ट नहीं करेगा. व्हाई? थैंक्स फॉर रिमाइंडिंग मी.
नो प्रॉब्लम.
कौन सी फर्स्ट कंडीशन? Yes, initial condition cannot be satisfied on this interval because this interval does not contain zero.
सही है.
You got it?
Yes, yes.
Well, initial condition किस पे define है? X equal to 0 पे. X equal to 0 पे y 0 है ना, और y dash जो है 0 पे 1 है. अब इस इंटरवल में तो 0 है ही नहीं. You cannot take x equal to 0 on this interval. So you cannot have this initial condition on this interval. It's technically wrong because you are defining that this differential equation is defined on 2 to infinity and its initial condition is at 0, which is wrong. It is not possible because this interval does not contain 0. So you have to pick up this interval because it contains 0. The initial value of the condition must have in this interval.
Okay, sir. Thank you.
Okay. Okay. No. Because at x equal to 2, the equation is no longer a second order differential equation. Equation becomes 3y is equal to 0 at x equal to 2. This differential equation does not remain a second order differential equation only at x equal to 2. The differential equation should be defined at every value of x. The solution of differential equation must be continuous. It should not have any break. Okay. I hope you get it. Why we cannot take this interval because it doesn't contain the initial value of the domain. Okay, then next thing is 38. We have there are a couple of exercises and examples there in the notes. You can try them. Okay, next thing which I need to define is the differential operators. Let me define it quickly. Then at 8:45 we'll start the quiz. Differential operators. If we have a2 of x, for example, second order or first nth order, that differential equation, let me define it there maybe because it will help me not to write again the equation. This one. Now, if I introduce this notation dn by dxn is equal to dn, okay? means nth order derivative, this one. And you can say that d by dx is what? It is d power 1 because we have first derivative here. Okay. And d0 is what? It is nothing. No, not a derivative. Okay. So you can say d0 of y is y. In fact, there is no derivative. If we introduce this notation and we rewrite this differential equation, how can I write this thing? I can write this thing in a way: an of x dn y plus an minus 1 of x dn minus 1 of y plus so on plus d2y plus dy plus y or d0y, okay, equal to right inside f of x. Now I can take common y from here, from all these terms. Okay, I can take y as a common, and then I can write, let me write it over here so that you can see it. So this further can be written as an of x dn plus an minus 1 of x dn minus 1 plus so on plus d2 plus d1 plus 1 or d power 0. This thing into y is equal to f of x. Okay. Now this thing is, if we define it as L, then how can we write that problem in a short way? L of y is equal to f of x. Okay. With L is what? An of x dn plus so on plus b plus 1. This is called is an operator. Okay, and it is nth order operator, nth order linear operator, because this one. What is the highest order derivative involved in this? N. That's why we call it nth order. And this is linear because there is no non-linearity here. So it is nth order linear operator. Okay. So this is how we define operators. There are linear as well as non-linear operators we can define. But for the time being, this is a linear operator. If we have a second order problem, then we can define any operator. For example, in that equation, y double dash minus y is equal to 0. What is the operator? Operator could be d square minus 1 times y equal to 0. This is how we can define this differential equation. Okay, and if we have 2y double dash minus x y dash plus maybe cosine of x y equal to e raised power x, then how we can write operator in this equation? We can write 2d square minus xd plus cosine of x, this thing, times y equal to e raised power x. So this is your operator L. Okay. So in linear differential equations, we can define operators in this. Further, we'll do in the next lecture. Now, you guys can start the quiz. The quiz is available on the LMS in the quizzes and tests and quizzes section.